Hello everyone, welcome back to Random Matrix Theory. So this is one of the last topics of discussion. So in this in the videos to come, we'll discuss some examples of matrix models, some examples of multi matrix models, and possibly mention some areas in which we can apply these multi-matrix models. I'll come back to what they are in a bit, but until now we have dealt with one matrix models. That is, let's write it like this: one matrix model, that is a matrix integral with one matrix and whatever trace of Vm with one matrix. In the videos to come, we'll see some examples of multi-matrix models. And in case of the one matrix models, we have seen application in two-dimensional gravity, or even combinatorics problem, that is the graph counting problems, how it can help us draw graphs. We also understood how we can give them a topological analysis to matrix models or matrix integrals. So these are the applications that we have seen, that is in terms of the one matrix model. So now let us see of multi-matrix model. So consider the following two matrix integral, that is a matrix integral with two different matrices. Let's say they're M1 and M2, and trace of M1 squared plus M2 squared, and we have our interaction terms. This is an example of multi-matrix models, and here we have, if you give them a graphical picture, a graphical representation, there you have two different kinds of vertices, and with this we can even calculate some important stuff like correlation functions and so on. Even from this, it's very easy, it's just a generalization of the one matrix model. Now if you notice this integral, let's give this integral star. If we tweak this matrix integral a bit, then we can describe something called the Ising model. Tweaking this a bit, we can describe the Ising model. So Ising model on a random surface, of course. So Ising, you might have encountered Ising model in a solid state course, in probably statistical mechanics course, or in any condensed matter course you encountered this. And the application of Ising model I've seen in different areas of physics and even outside physics. So for those who haven't encountered Ising model, so a word about Ising model is It's a model of spins. You know the spin of electrons or fermions. Spin up, down. These are the two possible spin of electrons for fermions. And this model describes, the Ising model describes ferromagnetic properties, interaction of spin, and so on. So I can give you an example of how the Ising model looks like. So lattice version. Let's see. Let me give you an example of the Ising model, how the Ising model looks like. It's similar to placing, the lattice version of the Ising model is basically placing different different spins in different corners of a lattice. Since here you have a somewhat a lattice-like structure, so let's say this is a lattice, and you place different spins on a lattice, and you study their interaction, phase transitions, and so on. There's also a Hamiltonian dedicated to Ising model. Basically we do physics of the Ising model. That is what is done when we study about the Ising model. So interactions, phase transitions, and so on. If you want, you can Google this up, the Ising model, and you'll get an analysis. But when you encounter this in a higher level course, or even in statistical mechanics, you understand how the Ising model helps us in describing different physics. So coming back, how do we apply the two matrix integral to describe the Ising model? So I claim that the following two matrix integral describes the Ising model. I'll try to give an intuitive analysis. Proving this is beyond the scope of this course, so I'll try to give you an intuitive analysis of how it describes the Ising model. It's similar, but we have this term here and exponential g1. So a question is, how does this differ from our previous matrix integral? We'll see this in a bit. But first, let's see the two terms trace of m1 cubed and trace of m2 cubed corresponds to two different vertices. Let's give them different colors. This is trace, let's say trace of m1 cubed. This is trace of m2 cubed. Since you notice that there are two possible spins, up and down, we have two different variables to describe the up and down. So one of them can describe a spin up and spin down. The other can describe spin down. This is how, studying this in different potential settings or on a random surface, using this matrix integral, you can describe Ising model and their interactions, that is the interaction between spins, and by this matrix integral. And the mixed term that you notice here, this mixed term describes their interaction, that is how the different spins interact. You'll see this in a bit. So mixed terms of M1 M2, the correlation functions. When you do the correlation functions, these mixed terms, that is how spin up or spin down, or how M1 and M2 are related, that is the propagator between them, will describe the interaction, and the interaction will be weighted by this term. We'll see this in a bit. So we can write the quadratic term like this. In terms of, let's say, in terms of this matrix C tilde, we can write our quadratic term, that is this term, inside the trace, and this is the quadratic term. We wrote it in terms of the matrix. If you see, if you multiply this out, you get the left hand side. So what is the inverse? Okay, let's first. Okay, what is the inverse of C? That is the inverse of C. If you do it, it's something like this. It's the determinant, and you exchange the diagonal. You exchange the diagonal elements, off diagonal elements, and a negative sign in front of the off diagonal elements. So this is what you get if you do the inverse. And let me remind you something. If you remember how our correlation functions were set up, they looked something like this. That is inverse of matrix A. That is, if you do this, it's this A. It's the inverse of this matrix A. This is how the matrix A enters our correlation function. If you remember it, we have done a whole analysis. So this is how our C term, that is this term, enters our correlation functions, and that is how the correlation functions of our two matrix integrals will be affected. So if you remember, the propagator is M alpha, because alpha can be 1 or 2. We have two matrices here, 1, 2. So alpha, let's give them alpha and beta can be 1 or 2. Right? It can be M1 M1 or M2 M2 or M1 M2, whatever the combination. So since we have two matrices, that is the case. And again, it can be IJ or KL. So now delta IL delta JK times 1 if alpha equal to beta, C if alpha not equal to beta. Why is that? Just look at this term. This is the inverse, this term. If it's off diagonal, that is if it's M1 M2, then we have, that is if alpha not equals beta, then we have C, and if it's equal to beta, then we have 1. The diagonal elements are 1. That's how things set up in here. And so let me give you an example of planar graphs of this two matrix model. Planar graph. Planar graphs are graphs that you can draw on a sphere or G in a zero surface. So our let's straighten them up. So okay, and the other vertex was red. So this is a planar graph of this two matrix model, and since each propagator is weighted by 1 over 1 minus c squared, so each of the propagators will be weighted by 1 over 1 minus c squared. Propagators are edges connecting themselves. So if you remember, it's the edge, that is, if I'm connecting something, that is a propagator. So this is a propagator, and for double line it's like this. For double line graphs or for matrix models, it's double line graphs. So this is one example of a multi-matrix model. Here you have where we have considered two matrix models, that is a matrix model with two different matrices, and as I said, it describes the Ising model, and we had, and because of the interactions, of those different spins or different vertices will be weighted by some factor. So for that, I have a C term, and it can be different depending. For the Ising model, it can be different for example, a lattice setup or two-dimensional setup or a three-dimensional setup. It will depend on what Ising model you're considering, and that's why we have put a constant C in our matrix integral, that is here. And by this you can describe an Ising model on a random surface. So let's see another example. These problems that I'm drawing of different colors, these are sometimes called color coding problems. So let me write it of a color coding problems. It's called color coding because they can describe the mixing of different type of things. For example, here spin up and spin down mixed, that is, we describe their interactions and so on. And you might have a different setup in the sense that you might have three different matrices, that is three different kinds of things. They're mixing described by this matrix integral. This is how you do stuff in the matrix integral. You can describe, for example, the correlation functions, that how different three things are correlated, how they are related to one another, and so on. And it's sort of like linking things. So let's see an example of a color coding problem, and in this scenario we'll consider three different type of matrices. So the matrix integral trace a squared plus b squared plus c squared, and n over 2 trace of ABC plus ACB. So since we have three different kinds of stuff, we can assign a different color to each propagator. Trace of a squared b squared, okay, trace of b squared and trace of c squared. We can assign them different colors in the sense that let's see how a vertex will be in this matrix integral setup. So you have ABC and ACB. Let's see. So let's say A is blue, B is, let's say, this color, and C is red. And again, you might have a different setup. So A was blue, C, B. So if we expand the integral, you will get two different kinds of vertices, and this is how the vertices will be. And each propagator, we have assigned a different color to it. You can do all sort of linking problems with this type of matrix integral. You can link things, form a surface. You can do all kinds of stuff with this multiple or multi-matrix model integral. And for three things, you have more degrees of freedom. That is, you have more variables, you have more freedom in the sense that you can cover a surface, you can make polygons, you can make a lot of things with this matrix integral. So this was a brief on multi-matrix integral, and in the next video we'll try to study non-Hermitian matrix models. Thank you.